Okay, good afternoon. I don't know if it was announced, but Professor Bouman is traveling for a very worthy cause. He's trying to ensure that his graduate students can put food on the table. But he should be back. He will be back on Wednesday. So I'm going to continue. I guess he left off at last time he talked about decimation and got through most of this upsampling as well, but he didn't quite finish it. So what I'm going to do is a quick review of this, just to since it's Monday, and finish this up. It shouldn't take so long. But just as a quick review, the problem of upsampling is basically one where you've sampled a signal, and it's the problem where if you have let me say first that generally here we're interested in images, but when you go from 1D to 2D, it's a very straightforward extension, so it's just simpler to talk about the theory in 1D first and then extend it. But it's the problem where, like in an image where if you want to resize it, resize an image on a display, you have to change the number of pixels, and so you're going to have to somehow change the resolution. So in the simple 1D example, this sinusoid that's been sampled, the goal is to get another sample, get another signal that is as though it was obtained from the original analog signal with a higher sampling rate. And it can be described in a couple of very relatively simple steps. Getting that exact signal, assuming the original signal is band limited. And so the two simple steps are the following. He kind of went through this, so I should maybe go kind of quickly. But you can look at this as inserting zeros between the original samples of your original. And then the objective from there is to change those zeros to interpolated samples in between the original samples that were in the original signal up here. And it's most easily described in the frequency domain, because that process of inserting zeros is very simply a compression of the frequency axis of the DTFT. So our original signal is X, and then our upsampled is Y. The relationship in the frequency domain, when we insert zeros, is just simply compressing the frequency axis. So if this were the DTFT of the original X, and this is the is this L equal 3? It's just simply a compression by a factor of L. And this original signal is periodic with period 2 pi, so you'll get these replications now in the signal that has the zeros inserted. These other components that we call aliases. Now, the original signal, if we were to sample that original analog signal at a higher sampling rate, what we would see is basically just that center component, and we'd have zero outside that range. And so the way you can look at changing those zeros to interpolated samples is just by simply applying an ideal low-pass filter to this to remove these components. So that's depicted in the next figure. Yeah. So if we zero those out, we'll get interpolated samples. Show a quick preview. In the time domain, it'll change it, like that. So this is our zero inserted. We apply the filter, and we get nice, smooth interpolated samples between the original one. So in looking at what the corresponding filter would have to be, if we use an ideal low-pass filter, the corresponding impulse response of that filter is given by basically a sampling of a sinc function. And this is an impulse response that has infinite support. So in practice, it's not used, and so we'll talk about different ways of approximating this. But this would be the ideal case. It's a filter that has infinite support. So if you have your original signal, it has some particular length n, in order to compute each output, you're going to have to do, order n multiplies. So this will, applying this filter would be an order n squared operation, so it's usually not used. But in the ideal case, that's what you get. Now, so extending this to 2D now, it's very straightforward. It's just simply, just as before, inserting zeros in the between the original image sample. So maybe I should draw a picture. So the zero insertion you can depict by something like this. So let's say these are the original. I'll just do the, let me do the L equal 2. In the L equal 2 example, for upsampling by a factor of 2, we just insert zeros between all the original samples. And so the structure would, whoops, that should be a 0. The structure will look something like this. So something like that. So these are the original pixels, and these are the zeros. Okay. So that's basically just describing this operation. This is a fancy way of writing it by a bunch of shifted delta functions that are scaled by the original signal. The frequency domain representation would be of this for this filter, for the ideal case, it would just be a separable P-rect filter where the width is 2 pi over L. So in the frequency domain, it would be looking at it from above. If we draw, the mu axis and nu axis, and we're looking at it from above, it'll be constant in this region, and it has cutoffs of pi over L, minus pi over L, minus pi over L, pi over L, like that. And then you'll have, your, you'll fall between minus pi and pi, and then this, of course, repeats because we're dealing with the discrete space Fourier transform here. Okay, so that would be the ideal frequency response in 2D. The corresponding impulse response will also be that same kind of a sampled sinc function, this separable sinc function. And just like before, as I just mentioned a second ago, this is a function that has infinite support. Okay, so really, in general, to compute a single output pixel, you'd have to do an infinite number of multiplies of the input signal. Now, usually your input image has a finite spatial extent, right? It has just a certain finite number of pixels. So maybe it's not, in that case, it's not really infinite computation. But as I mentioned before, to compute each output pixel in this case, you would need to, for each output pixel, you would have to consider, incorporate all of the pixels from the original. So it's very much overkill. It's, in theory, that will give you the ideal interpolation. But there's approximations that you can use that use a lot less computation. And also from an intuitive standpoint, if you have an image and your upsampled version, you're trying to determine the pixel value here, you wouldn't expect that you would need to incorporate the value of a pixel way up on the other side of the image. Most likely this pixel is going to be determined by only by the nearby pixels. So using something that has this infinite support doesn't make a lot of intuitive sense either. So there are a couple of approximations that are generally used for this. One is, and the most simple one is pixel replication, which is, this is kind of a sample and hold process, but it's basically, when you insert these zeros, all these additional pixels you've created, you just carry, maybe I can draw it up here. So when you insert the zeros, you just simply carry this pixel value in the original image forward to these new pixels you've created. And you do that for, for each of the new pixels you've created. So in a sense, what you've done is, if you're looking at a display device like a digital monitor that displays pixels as, squares, effectively what you've done in this case is you've increased your pixel size. So it's something that it should produce. It should give you an image that looks approximately the same if you looked at this new image, from a far enough distance. It should be equivalent because you still have the same, each pixel value is represented by a square block. But if you're looking at the original image and the upsampled image, this using this pixel replication, it might not look very good compared to the original because these individual blocks will be visible. You'll be able to resolve each of them, and you'll have a blocky appearance. And so in theory, I guess one of the benefits of something like this is it requires basically no computation. You don't have to do any multiplies. You just carry the values forward. You can look at it in theory as there is an equivalent filter that does that operation, and it's one that has simply this impulse response, which would look like the filter kernel would just look like this, where this would be everything outside here would be zeros. So this would be this is for and this is for L equal 2. This is just specifically for L equal 2 case. So this, in this case, this would correspond to Mn equals 0. And so the reason for doing that is because you can then look at what would the frequency response of this corresponding filter be. Now, in the ideal case, what we want to do is remove those aliases that we get every pi over L, every 2 pi over L. So in the ideal case, we would have an ideal low-pass filter. This doesn't have quite that response. This would have something more of like a P-sync roll-off. Okay, so it won't remove these. Let me back. So many pages. So a filter like that would not actually remove these aliases. The filter would do something like this. So these aliases you get out here would be attenuated, but they wouldn't be cut off. So in theory, it's not giving you the best interpolation. Kind of as an intermediate, something that's probably the most common filter to use is bilinear interpolation. This is kind of intermediate in the sense that it's not quite as crude as pixel replication, but it's a small filter kernel, so that the amount of computation you need to do for bilinear interpolation is relatively small, and it can give you better results than the pixel replication. So this bilinear interpolation also has a very intuitive appeal to it. It's just simply a linear interpolation of nearby pixels. So let me kind of develop this a little bit. Let me describe what that response looks like. So the response is given by these triangle functions. So just writing that out a little more here. Let's see. So this that triangle function in general, in case if you haven't seen it in a while, I'll just draw it pictorially. It's just simply a function that has this shape, where this is -1, 1, and 1. So when we do, in this filter, what we're doing is we're basically sampling that function at every, integer value divided by L. And so let's say in the L equal 2 case, this triangle function evaluated m over 2 would just be, you get the values 1, 1/2, and 1/2 at 0, 1, and -1, and then zeros elsewhere. So the corresponding 2D filter kernel, this HMN, again for L equal 2, would look like the following. The center of the kernel would have a value of 1. It'd have 1/2 above and below it. to left and right. And you get just, this is just the separable form of this guy. You take this as a function of m times as a function of n, and you get this, and you multiply it by 1/2, you get, oops, should be 1/4, 1/4, 1/4, and 1/4. And 0's outside here. So this is what the filter kernel will look like for this. Now, as I said, this has a very intuitive appeal to it. So our, let me redraw this, 0 inserted version of the original image before upsampling. Okay, so again, these the filled-in dots are the original pixel values. These zeros are the new pixels that we've inserted in here. And so what we need to do is determine values for these that are interpolated in between. Now, if we apply this filter kernel to this image that has the zeros inserted in it, if the center of the filter kernel is on top of the the original pixel, you're just going to get the original pixel back, which is good because when you do this interpolation, you don't want to you'd want to have the same values from the original come out of the output of this thing. When you compute intermediate values, these zeros, when you compute the values of these, you can see that in these cases where you're in between the original samples, I can draw a set of zeros up here too. The only values that are going to come into play is this one and this one, and they're going to have weighting coefficients of 1/2. So it's just a simple weighting, in this case, an equal weighting of the two nearest pixels. If you're trying to compute this location of the output, the center's located over here, it's going to be, the filter is going to be centered over here, and you're going to have 4 terms basically in the convolution sum, these 4, and they're each going to have a weighting coefficient of 1/4. So again, it's just a simple equal weighting. Now, in the more general case where L is a bit higher and you have more zeros in between, basically the new pixel value is just a linear combination of the 4 nearest pixels, where the weighting coefficient is proportional to the proximity of the pixel to each of the nearby ones. So if the 0 is located closer to a certain pixel, it'll have a higher weighting. But they're always a linear weighting, and they sum to 1. But it only takes into account the 4 nearest pixels, unless you're right, unless you're computing the values right in between the original pixels. In that case, it only takes into account those 2 nearby ones. But in general, it's just going to look at the 4 nearest pixels, take a linear combination of them. So it has a very intuitive appeal to it. And I guess I mentioned, so again, it's not ideal because if you look at the frequency response of this, it's going to have approximately very loosely speaking, it'll be approximately a p-sync squared kind of a thing. So it's going to roll off faster than the frequency response will roll off faster than in the case where we did the pixel replication, because it'll have a square operation, and but it still, again, will not remove these aliases completely. It will attenuate them, but it won't remove them completely. So in theory, it's not going to give you the ideal response, but it's a very good trade-off. So this is a very common type of filter. Okay, so that's basically it. Are there any questions about interpolation? I guess we used up 20 minutes. Okay, so the next topic is image restoration. Now, we've kind of been, seems for quite a while, it's just the labs are slightly ahead of lectures, and this is no exception. According to the lab schedule, the lab that was due last Friday was basically the same topic, image restoration. So if you've done if you've completed that lab and if you read the lab document closely, then this is mostly going to be a review. It's mainly the same topic. We're going to talk eventually about, we're going to talk about first linear image restoration using linear FIR filters, and then we're going to look at a couple nonlinear cases, just as the lab does. And maybe I'll get through most of the linear part, and then probably on Wednesday the nonlinear sections will probably be finished up. Okay, so the general problem here is there's some image, some underlying image X, but perhaps in the when we acquired this image, when we measured it, or somewhere along the way, it has been corrupted by some process, and we're leaving this very general. It could be corrupted by noise, it could be corrupted by some kind of optical blurring, in a camera, for example, or this is left very general. It could be any kind of corruption. So what we have is this image Y, which is a distorted version of X. And the objective here is to try to use this information and try to get an estimate of this underlying image X. Now, in most cases, we won't be able to determine the underlying X exactly. And so we need to be a little bit, kind of clever and try to find an estimate of this that's as close to the original as possible. And we're going to talk about a very specific way of doing that we're going to look at in the context of a simple linear FIR filter applied to this Y, finding an estimate that minimizes the mean square error between the estimate and the original one. It's just a little bit of notation. So again, this is the general problem. Let's see. This is mostly notation, but one thing to note is that what we're, again, we have X is some underlying image. Y is the corrupted version. And from Y, we're gonna come up with some transformation, some function that gives us X hat. And this is what we call an estimate of the original X. So this thing is going to be determined by some function of the corrupted image. And the thing that we get out, we're denoting with X with a hat above it. It's just a standard notation. Now, what we're going to do more specifically, this more specific case we're going to look at, is our corrupted image. We want to estimate what the value of the underlying image X is at a particular lattice location S. And the way we're going to go about it is we're going to look at pixels in a surrounding neighborhood of S in the corrupted image, and try to determine, is there some function that we can apply to that set of pixel values to determine that single estimate at lattice location S. And so this is the more general case, where the estimate of X is determined by some general function of these pixel values in a window. That filter, or that transformation that you do, that could be, we want to try to find one. We want to try to find the transformation that makes this X hat as close to X as possible, and we're going to use the mean square error as a criterion for that minimization. Now, in some cases, that function can be a linear function of these pixel values, the pixel values in this window, or it could be nonlinear. What we are going to restrict ourselves to is specifically space invariant filters, whether it's linear or nonlinear. We're going to look at a transformation we can apply to a window to get our output that works over the entire image. So our filter will be constant. Our filter won't change with the location. It'll be spatially invariant. And so this is written in the more general context. Sometimes this, if you minimize the mean square error, you get something that's nonlinear. Sometimes it's linear. In what we're going to do carrying forward is we're going to look specifically at linear filters, and for a fairly good reason. Might need to back up a little bit, but actually, before I mention that, so as I've mentioned, we're using this minimum mean square error as a criterion for our optimization. Thank you. Now it can be, so what we're trying to minimize is this is something that's kind of not really in the notes. Not yet, so let me just kind of clear this. We want to minimize the expected error between the original pixel, or the underlying pixel value at lattice location S, and the estimate we make of it. So this is the minimum. This is the mean square error between the underlying pixel value and our estimate of it. Okay. So this is a mean square error. Now it can be shown. This step is kind of skipped in the notes. The minimum of this, the estimate of x of the pixel value has a very specific solution here. So minimize this mean square error. So let me just rewrite. Where again, this guy here is some function of pixels in the corrupted image in a window surrounding that pixel S. I guess I might have skipped over that notation a little bit, but this WS represents a set of pixels in a window around S, and this Y sub WS is a set of pixels in that window. So this is basically this is a vector of pixels. This is a whole set of pixels around S. So it can be shown that this is, in general, the solution to this minimum mean square error problem is the expected mean of XS given these pixels in the window surrounding location S. This is a general solution for this minimum mean square error problem. Okay, so he kind of jumps to that in this next slide. This can be shown without too much pain. I'm not going to do it here. I know he has students do it as an exercise in 641, and you've probably, if you've taken Stat 528, you've shown this. But I'm going to skip it here. Skip the proof of it here. So this is the general solution. So the minimum mean square error solution in general is this, as I just wrote. It's the expected mean. It's the conditional mean of the underlying pixel given the surrounding pixels in our corrupted version. Now, in the case where your X image and your Y corrupted image are both Gaussian, if they're jointly Gaussian, it can be shown that this conditional mean is given by a linear function of these, a linear combination basically of these Y pixels, the pixels in the corrupted image in a window surrounding location S. This is a general solution. This is a specific solution for when the images are Gaussian. Now, it's not always the case that you have Gaussian distributed images, but it ends up being so in cases where they're not Gaussian, the solution to this expectation will be, in general, not a linear function. It doesn't have to be. So, but even in the case where, and most likely the images that you're dealing with won't be Gaussian. Maybe if you're lucky, maybe they're close, whatever the corruption is. The original image data in X and the what's ever due to the corruption in the Y, most cases they're not Gaussian. So that won't necessarily hold in general, but it still can give you a decent result. So it's not necessarily the minimum mean square error solution if you restrict yourself to a linear, to some kind of a linear filter, but that's what we're going to do. Okay, so I guess this is just a little more notation. I guess I've already mentioned some of this, but let me go through it because we're going to define some vectors here that are going to be used in our solution. Okay. So I mentioned before, WS is just a notation for a set of pixels around, set of lattice locations around the location S. And the number of pixels in this window that we're going to consider is given by P. Okay, so so this W is just a set of lattice locations. This is written as, these are all written as, this notation. These are all surrounding S. So S is in this set, and all these R's are like offsets from S. These R1, R2, they're all offsets from that base location. So we're going to define these row vectors that are the set of values from the corrupted image at these locations around pixel S, and a set of filter coefficients theta, such that if we multiply these values by these thetas and add up the results, that's what we're going to use for our estimate. And so the objective is going to be to find the optimal set of thetas to give us the best solution. Okay, so using that notation, our estimate is given by just the inner product. Actually, I should also mention, if you're working from your notes, this theta should be a column, just from the matrix notation we're going to use. So there's a transpose missing on this. So our estimate is going to be a linear, our estimate of the underlying image at location S is just going to be given by a linear combination of these pixels. We're going to restrict ourselves to a linear FIR filter, and these are the corresponding filter locations, filter coefficients. So using that notation, we can just write this as a simple inner product. So the ZS is a row vector of the Y's, and theta is the column vector of the filter coefficients. That's our estimate. So the minimum mean square error, so the mean square error is just given by the difference. And what we're going to need to do is find the set of thetas that will minimize this. Now, so what we'll essentially be able to do is we're gonna estimate this expectation by using the sample mean, and we can do the minimization by just taking the derivative of that, setting it equal, or effectively taking the gradient with respect to theta and setting that equal to 0, and that'll give us our solution. So a little more notation for the problem, like we did in the lab. Okay, so let me back up, and from this, as I just mentioned, so the minimum mean square error solution is we need to minimize this expectation. Now, really, to do this exactly, you would need to have the probability distributions of X and Y. You'd have in order to compute this exactly. We're not going to do that. Instead, what we're going to do is use training data and estimate this mean just by using the sample mean. So we're going to do that using a subset of, we're going to do that by training using a subset of pixels out out of a particular image, and then perhaps you can use multiple images that have the same sort of corruption to train and find the best set of thetas. But we're not generally going to use every single pixel in the original images. Where, like you did in the lab, you selected a subset. You sampled like every 20th sample. So that's what this S0 is. So the original full set of pixels is S. We're going to choose a subset of those pixels in order to train, in order to find this set of thetas. And you know, another reason for selecting a subset is you generally want to steer clear of boundaries, because pixels that are near the boundary of the image, you know, if you have your image, and our objective here is to train, and we want to try to find the best, you know, set of filter coefficients to determine this pixel. If we train using the boundary pixels, we don't have any sort of image data to work with from out here. These are all effectively zeros, and so it basically messes up your estimate. So you want to steer clear of the borders. Okay, so continuing on this with our notation. So these Z's are row vectors that were defined back here. So this Z sub S is a row vector containing the pixel values from the corrupted image in a window surrounding lattice location S. I know I've said that several times, but it's worth repeating. So what we have in Z is we're forming a matrix by stacking these row vectors one on top of each other. So each of these Z's is it's a set of pixels from Y around this particular lattice location S1, around S2, and so on. And then we form the corresponding vector X, which contains the pixels at the center of that window from the uncorrupted version. Okay, so these are the original underlying. This is the original underlying image before it's corrupted, and we're going to estimate. We're going to try to estimate those values, and our estimates will represent with this column vector X hat. And what we would like to have is for these two vectors to match very closely, in some sense. And so what we'd like to have is we'd like to have these approximately equal to each other. So we need to try to, you know, find thetas to minimize the difference between those two. So in the least squares problem, just as was written before, the mean square error between these is the original pixel value minus the estimate, which is given by this inner product of the thetas and the corrupted pixels. Now, going from here to here, this is where we're dealing with the fact that we most likely don't have the distribution of the probability distribution of both X and Z, so that we can't get this expectation exactly. So we're going to approximate it by using essentially the sample mean of this quantity, the original pixel value, or the underlying pixel value minus the estimate. Okay. So we just sum those squared errors up, divide by the number that we use, and that's what we'll use to estimate this mean square error. Using the matrix notation that was just defined, we can write this as the norm squared of these this vector. Again, this X is a column vector of pixels from the original image, and this is the column vector of the estimates. And so this is just the norm squared of that vector divided by n. So now it's in a form that we can take derivatives and set equal to 0. And this, so if we I should make another point. If we minimize this function, if we do this minimization, this is known as a least squares filter. This differs in a subtle way from mean square error, only because we're doing this because we're estimating this mean given this. So the mean square error is there's a slight difference between when we say mean square error, we're talking about minimizing this. The minimum mean square error filter would be one that minimizes this guy. A least squares filter would be one that minimizes this error where we've used an approximation to that mean. Okay. Okay, so it simplifies the problem a little bit to do a little bit of math on that argument, the expression that we're trying to minimize, and this 1 over n0 is a constant, so it really shouldn't, it doesn't need to play a part, but it's left in this derivation because the terms that we get out of here have kind of a very familiar form to us, ones that you've seen in a previous lab. I guess it was back at lab 3 when you dealt with eigenimages. You dealt with terms that look similar to these. So the norm squared, again, these are vectors, so we can represent the norm squared by taking, you can represent the inner product, in this way. And so this is just some manipulation, and what we get out of this is basically two terms, where one contains this thing, which has a form very similar to an estimate of an autocorrelation matrix. So we give this a particular notation of RZZ hat. It looks like an estimate of the correlation between samples in this, basically between the pixels in our corrupted image, those pixels in that window, the autocorrelation between that set of elements. And this also similarly has the notion of an estimate of the correlation between the original, the underlying center pixel in the uncorrupted version and all the pixels in the corrupted Y image around it. So both of these are basically correlation estimates. That's an autocorrelation between Z and itself. This looks like a correlation between Z and X. So we'll give it this notation. So maybe I should write that down. So this is an estimate. Oops. Of the correlation between XS and the various, say, Y's in that window around pixel lattice location S. Okay. Okay, so this is basically just sort of restating what I just said. If you look at this, this has a very similar structure to a autocorrelation estimate, where each of these will be a. Let's see how many pixels do we have in Z. So this will be a P by P. Each of these will be a P by P matrix, and you're essentially averaging them. So similar to this is also P by P. And then the autocorrelation estimate, it's the estimate of the correlation between X sub S and all the Y's. So this will give us a, let's see. I guess this gives a column vector, no? Yeah. So this gives us a column vector of those estimates of those correlations. And so we can rewrite where is it? Oh, it's the previous page. So we can rewrite this, this expression by using that notation with this simple form. So what we can do in this case, these terms are this cost function. It's a function of theta. It has a very relatively simple form. This has the form of a quadratic in theta, and this is just a linear function of theta. So we can take derivatives of this very easily and set them equal to 0. I guess this isn't anything new. This is just, again, describing these. This is just showing that these are unbiased estimates of the true autocorrelation and true correlation vectors. So taking derivatives, essentially, we take of this cost function, we take the gradient with respect to theta and set it equal to 0. And the solution that we'll get out of that, if you, I guess there's probably a couple worthwhile things to note, and very useful to put it the notebook of every class that you have, and that is that for this, taking the gradient with respect to this this is very common. This is a very common sort of a term that you have to minimize, and so you've probably seen this. But if you take the gradient with respect to theta of, in general, if you have theta transpose times some matrix A times theta, the general solution to this, the solution to this for a general A is you'd have A plus A transpose times theta. Now, if A is a symmetric matrix, if these are equal to each other, this will be just equal to 2 times A times theta. And so that's, if A is symmetric. Okay, so and when you're dealing with this autocorrelation matrix, this is a symmetric matrix. So when we take the gradient with respect to that term, we get 2 RZZ times theta. We take the gradient with respect to the second term. We can use this formula number 2, important formula number 2. And that's if you take the gradient of theta transpose times some column vector A, you just get the column vector A back. So I guess if this is... Okay, so we take the gradient with respect to this term, and we just get 2 times this correlation vector. Okay, so setting that equal to 0, you get this, which is a very standard solution when you're dealing with least squares problems. So you estimate that autocorrelation, take its inverse, multiply it by that correlation vector, and that gives you the optimal coefficients in the least square sense. Okay, so just as a summary, for this problem, you define that matrix Z and the corresponding vector of x's. You compute these, and that's simply the solution to this. Now, we're not going to have... Yeah, go ahead.
We already have the pixel values of the underlying image of x and z. We need to recover it from the graph.
Unfortunately, I'm going to run out of time, but that's a really good point. So the idea here is that there's some kind of corruption process. We have this underlying thing, it corrupts it, and we get a y. Now, in order to determine this filter in this way, we have to have both x and y. So it's like, what's the point if we already have x? Well, the idea is that we want to find a filter that will apply to other images that have been corrupted by this same thing, which we don't have the underlying image for. So it gets to a very important topic, which is training. And time's almost up, so Professor Bouman's going to have to carry that on. But it's a very common theme in image processing, is sorts of problems where you find some image transformation from some set of training data, and so that will then be extended to other other images that have similar corruption. So I didn't quite get to that, but that's the next topic. So I'm sure Professor Bouman will say something about that. So thank you.